Okay, let's talk about work. Work. So in everyday life, we mean something when we say work. Can anyone give me a little bit of an explanation of what you would say work is as a non-physics person? What does work mean? So one sort of lay person's example would be putting in a physical effort to achieve a goal. All right, sure, something along those lines, right? You go to the gym, you work out, you do work, you get sweaty, and then you get super tight abs, or whatever. So that's the everyday definition of work. Physicists have a different definition of work. Um, okay, so work. Well, I'm going to define work for you mathematically, and then we'll talk about what it means. Okay, so for example, let's say, no, I don't like that. I want this. Okay, let's say I want to move an object. Okay, so in physics, work involves making something move. Okay, so work involves motion in physics. So in this case, let's say I want to slide a box along a tabletop. Okay, so I'm going to have to do something to make that box move, right? And this is assuming that there's some frictional coefficient here. In other words, there's friction. So I need to push this box with friction acting on it, right? To make that box move or to keep it moving some distance, which we'll call S, I need to apply a force, right? So I need to get behind this thing. And if I want to make it move at a constant velocity, then I'm going to have to push it, right? Constantly the whole time, the force, all right? So the definition of work then is force acting over a distance. Okay, so force times a distance, and we call this work. W equals F times S. Now that's not the whole story. That's the basic idea behind this. Okay, so it has the ability to apply a force over a distance. Okay, so the ability to push something along a surface. Okay, so it involves force and it involves a distance. So there's a little more to this, and actually, it's kind of an interesting little scenario that we have here. So it's only considered work when the force is in the same direction as the motion. Okay, so what do I mean by that? So we have to slightly modify this. This is the simplest kind of form, and I think it sort of makes sense that we do work as force times distance. And actually, just before we move on, let's figure out what units we'd be working and what units we would be creating here. So if I think about it, and I just look at the units, I've got newtons and I've got meters here. So one way of looking at work is in the term Newton meter. Okay, so let's say that I did a 10 Newton force times a 10 meter distance. Well, then I would have done 100 Newton meters of work. Okay, now the Newton meter actually is also called something else. Does anybody know what it is? The joule, right, the joule. It's also called the joule, so AKA the joule, also known as the joule. So James Joule, I guess early physicist, should probably bone up on my history, not sure exactly what he's famous for. I know a little bit more about Watt, but we'll talk about that later. Okay, so let's just figure out what base units this drops down into. So we've got our MKS system here, right? So remember, a Newton is kilogram meters per second squared times meters, right? So then we can get that we have this as the base units for joules. Okay, so that's known as the joule or the Newton meter. You see it in both forms, but more often just as joules. Okay. All right, so that's the SI proper definition of work, as well as energy, and we'll get there in a minute. But before we do, let's talk more about this whole direction thing. So there's this, I don't want to get too much into it, but there's this concept of what's called a dot product. And this is when you get into sort of, I guess, higher level physics. And it's a way of dealing with vectors and not vectors. So you may think that this would produce a vector value, but it actually doesn't. You can have positive and negative work. However, that doesn't mean that it has a direction in the same sense that, say, like a velocity does. Okay, and that gets a little confusing. But here's a way to sort of help you think about that. Let's imagine that this is a dock. Okay, this is a dock, and like let's say we have a boat in the water here. Okay, and let's say that you are pulling a rope at, say, like an angle like this, and then that the boat is moving here like that, right? Because it can't move into the shore because there's something like preventing it, right? So in this case, we're applying a force that is not in the exact same direction, right, as the distance that the boat is moving, right? So how do we deal with this? We can't just go force times distance because they don't point in the same direction. So what we do is we actually only count the portion or the component of force that's acting in the direction of motion. Okay? So in order to do that, we project, if you want, part of the force that is actually causing the motion in this direction. So that would be from this angle the cosine of force, right? So F cos theta is the portion of this that's acting in that direction. One way to think about that is if you were to say, like, shine a bright light on here. That's a light bulb there. Okay, shine a bright light on here. It would be the shadow, right, of this line in this direction. This is a way to multiply vectors, and it's technically called the dot product of force and distance. But what you end up with at the end is you end up with this as a better definition. So you get F cos theta, but we're just going to move it to the end, S cos theta. Okay, so now what we're saying is we only count the part of force that is in the direction of distance. Okay, and that's what the cosine does for you here, and that's why you see it written this way. All right, so if you're pulling at a different angle than motion, we only count part of that as going into the work of the system. Okay, so now let's add in this concept, and then we'll wrap it up. Okay, so work, energy, theorem. So what this is a way and a way to think about work and energy and how they relate to each other and what energy actually is. So first, let's define energy. So energy is the potential to do work. Potential to do work. And we're going to use a little example here, okay? Let's say I did this. Let's say I took a heavy block and I lifted it up high. Let's see here. Okay, so it's sitting on a surface and I somehow lift it up. I put it up high, okay? And actually, let's make it even more realistic here. Let's take a pulley and do it with a pulley. So put that there. Let's say we're even like maybe we're pulling up over here. Okay, so here's a surface. Now here I am. I've got this like over my shoulder. I don't know how I would do this. I'm applying a force in this direction times some distance, right? First of all, how much force do I need to get this moving upward at a constant velocity? How much force do I need? What force do I need to apply? And assume this is no friction. No friction. How much force do I need to get that thing to move up constantly? So just got to think about how much tension there would be, right? Don't don't look at this as an acceleration though, right? Just look at it as a constant motion. So in other words, if it's moving constantly upward, right, it's exactly the same as it's sitting still. All the forces are balanced. It moves constantly upward according to Newton's first law, right? If there's zero net force on it, which there would be. So we think about what forces are present. Well, we've got to have a downward force, right? What's that? What's that caused by? Caused by gravity. And what do we call it? Well, we call it the weight. That's confusing. Let's not use W for that. Just call it Fg down equals m times g. So how much upward force then would I have in the tension and thereby in the force that I'm having here? Well, I would just, Ft must equal mg, right? It's moving constantly. F net must be equal to 0 if there's no acceleration. So I'm just applying a force equal and opposite to gravity, right? Over some distance, okay? And that is moving this up some distance. So I'm working over here to lift this thing up, right? So we could look at it this way. It lifted some distance with some force. So I could say this. I could say that the work I had to do is equal to F times D. I'm working in the same direction, right? This is changing the direction of my work, but really, right, the tension in the rope is what's working directly on this object. I'm just applying it at a right angle by using this pulley, okay? So then we could say this, couldn't we? We could say that it's M, G, and let's not call this D because it's something special, right? It's the height that I'm moving. So let's call it H, MGH, right? The amount of work that I did is, the upward force I needed to apply, which is equal and opposite to gravity, that's mg. And then whatever height I went and I moved it over, right? So that's my FD. Here's my F, and here's my D. Okay, so that's how much work I did. Right? Does that make sense? So now think about it. Now that I've lifted it up, I'm now holding it still, right? Could this lifted object now do work for me back out? So if you think about it, right? We were to say attach some other object to here that's maybe a little bit less, has a little bit lower weight to it, but there's some friction here. Well, this lifted weight could like pull this back the other way, couldn't it? So it could do work. Once I've put work into a system, that system can do work back out the other way, couldn't it? All right, so we call this concept work energy theorem. Essentially what it says is, if I do work into a system, then that system can usually store, not always, but there's ways to make that system store the energy for me to use it later, okay? So doing work stores energy, okay, which is available to be used later, okay? And that stored work, that work we did, that store, we call that potential energy, okay? That's called potential energy. And there's different types. So in this case, we call this gravitational potential energy. Okay, so a lifted object has gravitational potential energy. You think about this in a lot of other ways too, right? Like if I have a big stone up in the air and I drop it onto, say, something like a nail, right? Well, that nail is going to be driven in. That's going to have a force times a distance, right? So this raised object, as it falls, can do work for me later, okay? So it's got gravitational potential up here. And if I let it fall, right? We'll talk about what happens with gaining a velocity if you have a mass, that's for later, but as it falls, you can imagine it could drive a nail in. It could provide a force over distance, or it could do work later, okay? Does that make sense? Okay, perfect. Well, let's talk about two more things, okay? There's two laws of thermodynamics here that we want to talk about, okay? Thermodynamics, I guess, like the name sounds, it's the dynamics of heat transfer, but really it applies in general to work and energy. The first is conservation of energy. So there's conservation laws all over physics, right? Momentum and energy. Okay, so conservation of energy, and basically all it says is in a system, no energy is ever gained or lost. Okay, and the second is that in any energy transfer, so when I say energy transfer, that would be a case like we just talked about. Object up high, falls, I'm trying to make it do work later on, right? In any energy transfer, some energy is lost to the environment. So how is it lost? Well, it's lost in many ways. One way could be heat, maybe sound, maybe just to kinetic energy of molecules. I guess that's heat. Friction, these are all related. Okay. Basically, they're lost to the environment, into molecules in the environment. Okay. We often in physics ignore the second law to make the math easier. Okay. And this is just when learning. Okay, so we say, we have this much energy here. What can we do with it? So let's do a quick example and then we're done. Okay, so we're saying a 10-kilogram ball is lifted 4 meters in the air. How much work is done? And then how much energy is stored in that system? So let's give it a try. Here's your ball. There's your 4 meters. Okay, so we want force times d, or in this case, height. So the amount of work we'd have to do then is mg times h again, right? So we need the force, we need to counteract the force of gravity, and we need to lift it up 4 meters. So we should have 10. Let's just use 10 for g to make it easier. And 4. So we should have 400 joules of work we're required to lift that ball. And we could also say for part B, now we have an EG of 400 joules. So later, we can drop this and get 400 joules worth of work back out of it. No energy gained or lost. Okay, that's conservation of energy. However, in real life, because you're working through the air medium, because there's a potential for heat to transfer out into the environment, you would never have 100% efficiency in real life. Okay, but in our physics world, in our ideal world, we can say this. So the last question I want to ask you then is, like, what's the size of a joule? How can we get a picture of the size of a joule? Let's imagine that we're lifting an object. Okay, and let's say we lift it 1 meter. Okay, 1 meter. So we want to know what 1 joule worth of work is, right? So F times H, or mgh. If we lift an object 1 meter, what mass would it be in order that we end up with 1 joule at the end? Well, we'd want this to be 0.1 kgs, right? If we say that gravity is 10 meters per second squared, it's a little bit less than that, but just to make it kind of easy and visualize, let's imagine we lifted 100 grams, 1 meter, okay? If we did that, we get 1 times 1, or 1 joule worth of work. So I'm going to go grab a 100-gram mass and lift it a meter, and we can see what 1 joule worth of work looks like.